Section 2.2 is titled Basic Differentiation Rules. And what we're going to be looking at in this section is simplification rules or simpler rules of finding derivatives than you've been doing in 2.1. So what were we doing in 2.1 to find derivatives? Limits. It's the long way, right? It's this limit definition of derivative. And you will have to do just one of those on your test when we get there, okay? Everything else that we're going to do beyond this is actually rules that are based on, simplification rules that are based on that limit definition. Okay, so what happens when you do, the limit process enough with certain kinds of equations is patterns start to emerge, and you start to look at it and go, oh, it always works out like this. And if I notice a pattern, then is there a need for me to continue to do the same process over and over again? Well, there probably isn't. And so that's where this section is coming into play, is the noticing of patterns going on. So we're going to talk through these. Some of you have had calculus classes before, so you know them, so I'm going to rely on you to help me fill in the details. We'll see if you remember them correctly. You probably do. Do you remember, those of you who have had calculus before, when you have a constant, like y equal 5, and you take its derivative, what do you get? 0. Okay. And the basic idea is that let's think about a graph. We're going to think about a graph for this one and a couple others perhaps. If you have an equation that's a horizontal line, and remember, derivatives are slopes. What's the slope of that line? 0. That's it, right? It's 0. Your book doesn't do a sort of intermediate theorem between 2.2 and 2.3, but I'm going to just write it here at the bottom. Let's just say we'll call it theorem 2.2b. I don't know that I like that title, but we'll go with it. So let's say that we had a line. So f of x is equal to our favorite mx plus b, right? Slope line equation. If I have this equation, what's its derivative? It's m. And the easiest way to think about that is, remember, derivatives are slopes, right? What's the slope of mx plus b, the equation y equal mx plus b? M. So anytime you're dealing with a line, a linear equation, the slope is simply m in the equation. All right, power rule. So my husband took calculus when he was a freshman in college. He didn't do very well, but that's because I was 2 years behind him in school. If I had been right there with him, he would have done much better, I promise. So this is about the only thing, though, that he remembers from calculus is this rule right here, the power rule. So do you remember the power rule? Good, yeah. Seriously, I'm pretty sure if I were to ask him, this is the only thing he could tell you from calculus. So the power rule is that if you have x to the raised to the power of n, you kind of have this feeling that this n gets pulled down here in front, and then you decrease the power of n by 1. Okay? The next two rules are sort of like the limit rules that we had before. Everything that we kind of would hope would be true is. So this one right here says that if I have a constant, so a number times a function, what do I do? And all I have to do is I have to just take the derivative of the function. So the constant c stays, and the derivative of g of x is g prime. And this is one of those rules that you use it all the time, and you don't even sort of think about the fact that you're using it. I mean, and I'll point it out to you when we do it, and you'll be like, oh, well, okay. I mean, but you don't think about doing it as you do it. The next one is the same thing. When you have the sum or the difference, so you have the addition or the subtraction of two functions, you just take their derivatives independently and then add or subtract them together. So you have g prime of x plus or minus h prime of x. And again, I'll show you when we do it, but you're going to not even realize you're using it when you are, because it feels so natural to do what you're doing. All right, the last two that we're going to do today are the derivatives of sine and cosine. So does anybody remember the derivative of sine? Cosine. It's cosine. Yes, it is. And as much as I would like to write down the derivative of cosine as sine, it's not quite true. It's negative sine. Okay? So the reality here is this is about the only one when I was y'all's age that I kept in my mind as a rule. And that is, remember, the other one includes the negative. Derivative of sine is cosine. So anytime I wanted to do the other one, I knew it wasn't the one that was that way, and it was the negative one. Okay? So what we're going to do now is we're going to see a lot of not application questions, that's not exactly true, but we're going to do some very straightforward questions with this, and then we're going to do some variations of it. That's the word I wanted. All right, so we're going to start with x to the 7th. So this is a very straightforward power rule. All right? There's a 7 exponent, so what am I going to do with the 7? Bring it to the front. Okay, so notationally, actually, I'll write this out in a minute here, but this is what we've been using so far was this prime notation. So I'm going to bring the 7 down. I'm going to rewrite my x, and then what will the new exponent be? A 6. Very good. So let me pause right here and make mention of the fact that there's another way that I could write the notation instead of y prime. And it has some really nice features to writing it the other way. It's more cumbersome, right? Like it's messier looking, but it has some intuitiveness to it that's helpful. The other way that we could write y prime is it's the same thing as writing dy over dx. And your book really likes that dy dx notation. So if you go and you like check out on me and make sure that I gave you the right rules today or whatever, you're going to see dy dx's everywhere because your book uses that one frequently. The benefit to y prime is that it's so clean. Maybe a drawback to it is that sometimes that prime might start to look like a 1 or something. You might get that confused depending on what you're doing. The sort of drawback to the dy dx is it looks like there's some sort of a division going on. And in some sense there sort of is, but we're using it all together as a notation, like a name. The reason I say there sort of is a division going on is because, do you remember the equation for slope? What does the equation for slope look like? y2 minus y1 over x2 minus x1. Does anybody else remember another formula for this? There's a couple others. You could switch the x's and the y. I mean, not the x's and the y's, but the ordering of the y1, y1, y2s. Like you could switch that. There's one more. Sometimes you see somebody write this. Deltas. Did I write them upside down? That's because I've been doing calculus 4 more recently. How about like that then? Okay.
What's it upside down?
Gradient. You'll get there. Oh, maybe.
I'm only going to 2.
Oh, you could enjoy it so much that you could decide to take 3 or 4 just for fun. See?
University physics. Yeah.
All right, so do you see the notation similarities, though, between this and this? I mean, right? It's change in y over change in x, and that's slope, and that's what derivatives are. They're slopes, okay? So that's sort of the intuitiveness that I was talking about. Like, it has a meaning that really makes more sense than this prime notation that we use. But we like the prime notation because it's so convenient. All right, let's try another one. Okay, this one down here on number 2 has pi times cosine of t. Okay, so first of all, you got to recognize pi is just a number, right? Right? I mean, I know it's a Greek letter as well, but it's a constant. It's a number. So when we're looking at this, we're not going to actually do anything with the pi except for carry it along. This rule is actually rule 2.4, the constant multiplier rule. We're going to write down pi, and we're not going to do anything with it. Oops. So as I do my derivative here, the first thing I'm going to do is simply write down pi. And then I'm going to ask myself, and you're going to ask yourself, what's the derivative of cosine? Negative sign. I'm going to put the negative in front of the pi and the sign after it. If you want to put negative sign all together, that's okay, but make sure you put it in parentheses because we don't want this to look like pi minus sign. It's not pi minus sign. It's pi times negative sign. Okay? So be careful with your notation that it really means what you are intending for it to mean. Okay. What we're going to do next is we're going to take some that look a little bit like they don't fit the rules that we have, and we're going to change them so that we see that they really do fit the rules that we have so far. So the first thing we're going to do is we're going to rewrite this. So what about this, I didn't mean to prime there. What about this makes it not quite look like the rules we have?
It has 3x squared on the as a denominator.
Yeah, there's something about a denominator going on that makes it look not quite right. Agreed? Now, the 3 in the denominator is not a problem. That's a constant. It's the x squared in the denominator that's sort of the problem. So as I write this, I'm not going to do anything with the 3. It's going to stay in the denominator. I can't just move it. It is in the denominator for good. Okay? But I can change x squared using properties of exponents. How could I write x squared instead of x squared in the denominator?
Yeah, put it as x to the negative 2.
Right. I can write it as x to the negative 2. Do you remember that property of exponents? Yeah, I'm working with my elementary ed majors with some of those properties of exponents recently, reminding them of those as well. So I get to remind you guys too. All right, so the x squared that's in the denominator is now x to the negative 2 in the numerator. And the reason that's helpful is because I've got a power rule. It works for negatives just like it works for positives. So as I differentiate, remember that's the same thing as saying take the derivative, the 4/3 at the front stays 4/3. It doesn't change anything. What am I going to do with the negative 2? Bring it to the front. So I'm going to write this as multiplication. Whoops, I need a negative there. Let me try that again. Negative 2. And what will my new exponent be? Be careful. Negative 3. Not negative 1, right? Remember, we're subtracting negatives, so it needs to be getting smaller in a negative sense, which is a bigger looking number, negative 3. Simplify means we need to clean this up. So a couple of things that means. It means if there's any multiplication that can be cleaned up, we're going to do that. That's one of the things. The other thing is that we're going to make sure that our answer looks like the original question. So do you notice that original question? No negative exponents, right? So my answer is not going to have any negative exponents either. Which means instead of it being x to the negative 3, what am I going to have to do with it? Bring it back to the denominator as x cubed.
So are you never allowed to have negative exponents, or is that just we're doing it because that's what the original looked like?
It's because of what the original looked like. There's nothing wrong with negative exponents. Absolutely nothing. But we're going to mirror the way the problem started. Okay? Very good question. All right, so I'm going to put the negative on top. So this would be negative 8 on top. And then I've still got that 3 on bottom, and now it's x cubed. Does that look okay? Everybody good with that? Remember that negative 2 is like negative 2 over 1. Okay, so we're going to basically do this same thing without the guided columns for the next problem. So this does not look like the rules we have, and it is worse than the last problem, isn't it? Not only do I have an x to the 2 in the bottom, I've got some x's on top as well. It's really a lot cleaner than you might think. We're not going to do what we did in the last problem and just bring it up, because then I would end up with multiplication in the numerator, right? I'd have multiplication of this x to the negative 2 going on, and I don't have a rule for that yet either. We will on Wednesday, but we don't today, okay? And in fact, even though we will on Wednesday, it still wouldn't be the cleanest way to do the problem. What we're going to do right now is definitely the cleanest way to do the problem. So what we're going to do is we're going to use a rule for fractions that you know, but you're used to using it the other way around. We're going to separate out that numerator into 3 separate numerators, all over the denominator that we are given. Now, some of you probably don't even need to write this down. You're totally cool with the fact that I just said that and you knew what I meant, and that's fine. Some of you need to write it down because you didn't really catch what I was doing, and maybe you're not quite sure where I'm going with it, and that's okay. So this is a step you may or may not actually write. But what we're going to do is we're going to simplify each one of those fractions now. And a simplification that we use is going to allow us to use the rules we have. How about the first one? When I have x cubed over x squared, how does that simplify? That's x. How about 3x squared over x squared? Minus 3. Now, come on, those look really nice, right? Those are very clean reducing pieces. The next one doesn't do that though, right? There's no x in the numerator to cancel with the x in the denominator. So the best we can do is to make it look like the last problem we did. Is to raise it to the negative 2, exactly. So it'd be it would be 4x to the negative 2. Notice I put equals equals. Don't give this the name what is it called right now? G prime. Don't give this the name G prime. You didn't do that. All you've done so far is rewrite what you started with. All you've done so far is algebra. There's no calculus in there just yet, but we're about to have some calculus. Now we're ready to take the derivative of this guy. So, what is the derivative of x? It's 1. And why is it 1? You can do it that way, yes. So if you sort of brought the exponent of x down, it's a 1, and then you raise x to the power of 0. There's another way you can think about it too. Why else would it be 1? Huh? What? That's the same thing they were saying, yeah. What kind of equation is y equal x? It's a line, and it's line with slope of 1. And that's the cleanest way to think about it. It works both ways, but it's a line with slope 1. All right, so now what's the derivative of the minus 3? That's 0. You don't have to write it. I am just for the sake of having a placeholder for the moment, okay? So I'm going to put my minus 0, because we're going to clean something up in a minute anyway. How about that 4x to the negative 2? Okay, and so some of you are already jumping in, so I want to make mention of the fact that you used a rule and you didn't even sort of think about using it. Most of you just told me it was negative 8, and you told me some other stuff. I'll write it down in a minute. But why was it negative 8?
Because you took the derivative of, you brought the negative 2 and then multiplied by 4.
Yeah.
And then you changed the exponent to negative 2.
Yeah, let me write that down too since you're mentioning it. So in doing that, we actually did 2 steps in 1. We used that constant multiplier rule, that 4 in front, and we carried the 4 along for the ride, basically, right? And we used the power rule, and we kind of combined them, and we didn't even think about the fact that we were doing it. You just did it. You just multiplied it, okay? All right, so in cleaning this up, there's a couple of possibilities of how you could leave your answer. One possibility is not the way it is currently written, okay? What about this is not going to be okay for your answer to be left in? The negative exponent. The original problem didn't have any negative exponents, right? So your answer is not going to either. So one possibility is to simply return the x cubed to the denominator like this. And I'm totally fine with that being your answer and being left that way. If you check the back of the book, it might actually combine these two fractions, quote unquote, these two terms back into one common term, because the original problem kind of started that way too. So they might do something where they get a common denominator. Let me put this down here as or. And they might actually write this as x cubed over x cubed and then combine it so it's x cubed over 8 minus x cubed. The only reason I mention it is because I want you to recognize that if you looked at a back of a book or if you saw somebody else's answer online or if you were comparing with a friend and they did that, these two are actually the same answer and they're both equally right and acceptable. Okay? All right, any questions on that one? Okay, the next one's more fun. Those are radicals, aren't they? There was absolutely nothing in those rules that I gave you about radicals. So you may have to go back a little ways in your mind and try and remember, what in the world can we do with radicals to make them look more like the kinds of things we're dealing with in this section? Yeah. Okay, so Nate, tell me what the first one would look like.
X raised to the 1/3.
Fantastic. So the 1 is coming from the exponent that's currently on the x. I mean, we don't see anything, so it's an understood 1. And then 3 is coming from the index of the radical. So if that's what that one looks like, what would the next one look like? X to the 1/5. Okay, again, we didn't do any calculus. We just did a rewrite step of algebra. Now we get to do the calculus to take the derivative. So what's the derivative of x to the 1/3? Somebody? Okay, good. All right, so let me pause right here to think with you for a moment. When you do subtract fractions, sometimes people make mistakes. You just move through it very quickly. So be careful when you're subtracting your fractions. Occasionally I'll have somebody write down 1/3 turns into negative 1/3. Don't do that. Be careful that you really are subtracting the number 1. So the 1/3 comes down, then 1/3 minus 1 is negative 2/3. How about the 1/5? It comes down to, What will the new exponent be for that one? Negative 4/5. Here's a couple things. You're not going to leave the answer like that. The original answer didn't have any negatives, exponents, and it didn't have any fractions either, right? It had radicals. So we want to change this to be back in radical form. And the radical form necessitates that those exponents be positive. So how do I get the exponents to be positive? I move them down to the denominator. And then I can use the notation for radicals to change that as well. So I'll take it in a couple of steps just to make sure everybody's okay with this. So the first thing I'm going to do is to move this to the denominator, 2/3. It is possible that WebAssign will take this as an answer at this point. That's quite possible. When I'm looking for it on the quiz, I will guarantee you, like on Friday, that this is not going to be an okay place to stop. If it starts in radicals, you're going to end in radicals. Okay? So we're going to change this into radical form now. So it's radical form. The 2 stays with the square, with the x. Okay, it's staying an exponent, and then the 3 will become the cube root. So we have the cube root of x squared. And then we have 1/5 roots of x to the 4th. There's no need to sort of think, oh, maybe I should combine these together. Were they combined together to start with? No. So don't go doing more work than you need to. I'm already asking enough, right? Leave it where you can leave it. This is a good place to leave it. Okay, any questions on that one? All right, so here's one of the things I was talking about. This is a variation of what the other questions have asked so far. It says to find the slope of the graph. What does slope of the graph mean? Derivative. So when we see the phrase slope of the graph, it should trigger the word derivative in our minds. So find the derivative, but it says at the given point. How is that different? What do I have to do that I didn't have to do before? I'm going to have to plug something in. So I'm going to do the derivative like I did in the last problems, but then I'm going to plug something in. In particular, I'm going to plug in x, and they give me the x value. Not only that, they even give me a y value. I just don't need it. Okay? I'm going to plug in x because the variable is x. So I want you guys to find the derivative. Just write it down. We've already done ones harder than this one, so I know you can handle it. What would the derivative of 3x cubed minus 10 be? What was it, Josh? Okay, did everybody get that? 9x squared minus 0? Or if you prefer, just 9x squared is fine. Did everybody get that? Okay. I'm going to change my notation just a little bit, just because I like to be able to plug a value in. So this is kind of like f of x notation. I'm just going to put the parentheses next to it, because what I'm about to do is plug in the number, in this case 2. Right? Because they told me that the x value for the point that I'm looking for is x equal 2. So if I plug in 2, what do I get? 36. Just, that's a slope. It's a very big slope. It's a very steep line. Or not, yeah. The line created with that slope would be very steep. And that's happening because it's a cubic equation. Cubic equations, as you move out towards the end points, or the end behavior of those, are very, very steep. So that makes sense. Okay, same directions on this one. Find the slope of the graph at the given point. Oh, I'm sorry, there was one more direction on this one I just glossed right over. It says use the derivative feature of a graphing utility to confirm, that should say your results. Woo, typo. All right, your results. So what that's referring to is if you take your graph or your calculator, and you put in the original equation. So if you put in the equation y1 equals 3x cubed minus 10. Okay. And we're confirming that our answer is reasonable. We're not confirming that it's exact or correct. I mean, we're just confirming that it's a reasonable answer for what we've gotten. So I saw one of you drawing pictures in the air for me. Who was that? Was that you, Nate? Okay. So it looked something like this, right? Roughly. Does it even level out in the middle? Does it loop? Something like this, very, very steep.
Let me move my window down.
I'm just.
Okay, so all you're even seeing is this part of it.
Yeah, I moved my window down.
Oh, that's terrible. Oh, that's a good window. So eventually, this is a very steep one, isn't it? And let me draw in the axis based on what you've got.
New window work.
Terrible graph. Your calculator is so much better than I am. All right, so it looks something like this. And x equals 2 is going to be over here somewhere. So is it really, really steep? Yeah. If I drew a tangent line over here, would it have a slope that seems reasonable to be something as big as 36? It's going to be big. I mean, I don't know how big, but it's definitely positive, and it's definitely a larger number than, say, x equal 1, right, or m equal 1, which would be just a horizontal line like this, right? I didn't mean horizontal, a line like this, a diagonal line like this. All right, so let's do another one, same directions. But we have trig involved because trig's fun. Okay, so we've got f of theta. So I am not super particular and going to be persnickety about if you change those thetas into x's. Just make sure that they match within whatever line of text you're working on. So if you want to turn all those thetas into x's because it bothers you to write theta, I'm okay with that. But I'm going to use the thetas that are there. So it says to find the slope of the graph. Slope of the graph, we said means derivative, okay? And then it says at the given point, which means plug in the x value, okay? And then we're going to confirm that our graph makes sense of that. All right, so here's our equation, f of theta, and we're going to find f prime of theta. All right, so what would the derivative of 4 sine theta be? Very good. Yes, 4 cosine theta. And what would the derivative of the minus theta be? What was it, Jacoby? It's 1, a negative 1, because there's a negative in it, but it's 1. So theta is acting just like x, right? It's the variable. It's not a constant, it's a variable. Those Greek letters throw us off. You know, pi is a Greek letter and it's a constant, and theta is a Greek letter and it's a variable, so be careful. All right, so this is 4 cosine of theta minus 1, and then we're supposed to evaluate this at what x value? 0. Yeah, it is the point 0, 0, and the x value of that is actually the first 0. So we're going to plug in the number 0. If we haven't already done so, make sure it won't matter on this one, but make sure your calculator is in radian mode. You will not need it in degrees ever this semester. Okay, so make sure it's in radians. It doesn't matter on this problem because the radian and the degree value would give you the same thing. But what is the cosine of 0? It's 1. And then we have that 4 there, right? So this is 4 times 1 minus 1, which gives me 3. So my slope is 3. Okay, so we're going to use a calculator, a grapher, to confirm that that makes sense. So we're going to take our calculator and we're going to graph 4 sine of theta minus theta, or 4 sine x minus x. Oh, this is a fun graph. Ooh, we'll see how good I am at drawing. I'm terrible at drawing, so I'll just warn you now. Oh, that wasn't it.
So if you ask us to confirm it, are you going to want us to draw a graph?
I will, but it won't be on a problem quite like this. I'll show you what I mean. So when you're confirming on this right now, you're just confirming that the slope is reasonable. We're actually going to create equations of tangent lines in a little bit, and then confirming that makes a lot more sense than confirming this. Did I mess something up?
No, I was just saying it's right. I did the derivative.
You did the derivative when you plugged it in. Yeah, I'm going to show you guys how to do that too. I haven't got that far, but I'm glad you know how to use your calculator that way. Okay, so x equals 0 is right here. And this one actually has a slope of 3. Does it make sense that it's positive? Can you guys see that? That the tangent line's positive right here? That makes sense. It's bigger than 1 because that you could actually put in line y equal x and you could see what that line looks like, and it's definitely not sharp enough. So that makes sense. There is a feature in your calculator. We'll mention it right now since Nate brought it up. Is it under, yeah, math, calculate? Oh, calculate at the top, that's it. Okay, so if you hit second trace on your calculator, second trace, I'll write these down for those of you who want to make sure. You hit the second button, and then you hit the trace button. There's an option underneath there, number 6, that says dy dx. Okay, so if you select number 6, and then you can either hit the number 0 for x equals 0, or you can trace along your curve to wherever it is, and then it will tell you at the bottom what the calculation is. Now, your calculator is not using calculus to do this. Please understand that it's using a numerical method to do this. So my calculator does not say x equal 3. Mine says x equal 2 point, and I've got like 6 9s and then a 3. So you have to use a little bit of interpretive thought to say, okay, the calculator is actually wrong, and I'm right. But we're awfully close. Are you guys with me? So it confirmed for us that it's a reasonable answer as to what's going on, but it's still not quite right, and we are. So, all right, I believe we have one more question, 2 more questions, but I think we have time for one more. Okay, this one says find the slope of the graph of the, I think that there was a typo. I don't think I got this erased out. You mark that out. Okay, part A, find an equation of the tangent line to the graph of f at a given point. And then B, use the graphing utility to graph the function and its tangent line at that point. All right, so it's talking about tangent lines. Tangent lines talk about finding slope, okay? So we did this last time, or a couple times ago. We talked about an equation for a line. One form of that looks like this. Do you guys remember looking at this last time, or a couple times ago? All right, that's the point slope form of a line. They give us x1 and y1. The only thing we really don't know is m, that's slope, and the slope is the tangent, or is the derivative. So we need to find the derivative. So what in the fact is the derivative of x to the 4th? What's that one? 4x to the 3rd, good. What's the derivative of 3x squared? Negative 6x. And then the derivative of the 2? It's 0, yeah. Okay, and then in order to find the actual slope, what we need is we need this derivative evaluated at the x value that they give us, which was 2. So I need to plug in the number 2 into this derivative equation. So what do I get when I plug in 2 into this? What is it? 20. I agree. So coming back to the equation that we talked about up here, this is y minus the y1 value they give me, which is 6, equals m, which I just found, which is 20, times x minus x1, which they gave me, which is 2. And then we're going to simplify this to the y equal mx plus b form, the kind that you would use to put in your calculator, because actually, on this one, we actually need to put it in our calculator anyway. So as I simplify this, I'll distribute my 20. I have 20x minus 40. And then if I move the 6 to the other side, so I add the 6 to it, I get 34. So this is my tangent line. So last thing of the day, I want you to put the original equation in to y1, and I will put this one into y2. And I get that fun W curve. Did you guys get a W curve? Looks something like that. Don't judge my drawings. And then I'm going to put some color on mine because I have colors. And so the line that it does is over here. Looks like this. Yellow was a terrible choice on that. Sorry about that. Okay, any questions on that? Yes, Marco. Where did the what?
Where did, second equation come
This?
from? Yeah.
I distributed the 20 through, so 20x and then 20 times 2 would be the negative 40. The whole thing?
Yeah.
Came from the equation at the top. Y minus y1 equals m times x minus x1. So that's the point slope form of equation of a line. And then they gave me the x1, y1 value is 2, 6. And we found the slope value is 20. It's okay? All right. We have one more question in this section. We will do that next time. But we're pretty much done with this section. So I'm going to leave the homework to be due on Wednesday at midnight. We just have one little question left. So if you did all of your homework until you got to like the last 2 or 3 questions, I mean, you're set to do that. You have the ability to do that at this point, okay?